So this was the structure. It was clearly a steel structure. Some sections were given, but in the drawing, but I will talk about it later on. Basically, sections of the vertical members. Now, first task was, as usual, to perform the structural analysis of the two beams by plotting the diagrams of the internal forces, shear and bending moment as a function of P and L. And then determine the tension force in the tie and the compression force in the column as a function of P and L. Now, from the beginning, if you read carefully the text, you already knew what the solution had to look like, because it was clearly stated that there were two beams and that there was a tie and a column. Okay? So basically, we had two members subjected to bending moment and shear, one member subjected to pure tension, and one member subjected to pure compression. Now, without performing any calculation, what should I expect? I should expect that horizontal members are subjected to bending moment and shear. A vertical member that is below a beam is likely to be subjected to compression. This is usually the case, unless you have very fancy and very strange load combinations. For example, the whole load on one part with an intermediate support, which then makes a beam deflect, the other one lift up, which pulls basically a member. Weird case. In this case, where there is a distributed load, they should expect this column to be in compression. And of course, this vertical member, which is above the horizontal members, is likely to be in tension. So this is the tie, this is the column, and these are the two beams. Got it? Have you gone around Milan and basically the area of the park, of the Idroscalo Park? Very close to it is a very nice building. It was the home to the Mondadori firm, a big publishing company in Italy, one of the largest, one of the most important. Basically consists of an outer concrete frame with a steel structure in the middle, which is all suspended. So basically all with ties. If you've never been there, take a look at it. It's in Segrate. You can take a bike and have a ride to the Mondadori Sea. Just to tell you that usually we have columns, so vertical members which are below the portion where the load is, but you can also have ties when the structure is basically hanging from something which is above. Okay? Go and see it. Segrate, Mondadori are the keywords. Now, perform the structural analysis of the two beams. Differently from what I did in other written exams, here I explicitly demanded, or I asked you to go on and look at the beams, in a certain way suggesting you that there was the need to solve the whole structure, determine the reaction forces, and then go on to the single members. Why? Because, let me be clear about it, no matter what is around the beam, I mean, no matter the fact that here there is a hinge, here there is the rest of the structure, and for this beam here, there is a tie here, a column here, and also a beam here, both this and this are simply supported beams. As regards bending moment and shear, if you have a hinge and hinge, no matter what there is on the outside, it's a simply supported beam, okay? Which basically means to determine the bending moment and the shear in these two beams, I don't need to know everything about the structure. I just need to focus on what's happening on the beam. I can show it now to you. Let's start with AB. This is A and this is B. We have a distributed load, which is P. What are the most general forces we can have at the two boundaries? Here we have a hinge. It is hinged, fixed to the ground. So it gives you two reaction forces. One is horizontal and the other is vertical, because both the horizontal displacement and the vertical displacement are prevented. So VA, HA. Here we have another hinge, okay? A priori, since it's a hinge fixed to the rest of the structure, I have to assume that it behaves much like the first hinge, because generally speaking, a hinge transmits a horizontal force and a vertical force. Therefore, VB, HB. This is the most general situation in which this beam can be, okay? Now, what can we write about this beam? Well, we can write the three equilibrium equations concerning vertical, horizontal, and translation and rotation about 1 point, okay? Or you can also have other possible choices. For example, you can replace the translation equilibrium in the vertical direction by means of another rotation equilibrium. You know it, we've seen it, okay? Both choices are possible. So I will start by writing rotation equilibrium about point A, which is MA equal to 0. Now, everything that passes through this point does not give any contribution, because exactly, a moment is always the product between a force and the lever arm. If the force passes through the point which I use to write the rotation equilibrium, then the lever arm is 0, which means the moment is 0. So, no contributions whatsoever from these two forces, HA and VA. Then, for the sake of global equilibrium, and only for global equilibrium, I am allowed to represent the distributed load as its resultant force taking place at midspan, with a value which is P times L. So, since it's the distributed load, you take the magnitude of the load and you multiply it by the length. Very intuitive concept. And have to specify its distance from point A, which is L divided by 2. So the first contribution which I encounter as I move from the left to the right is PL times L divided by 2. By putting it positive, I am assuming implicitly that a clockwise moment is positive. Okay? As I said many times during the classes, during the course, it doesn't matter what convention you use. The only thing that matters is that you are consistent. So if clockwise is positive, then counterclockwise is negative. If clockwise is negative, then counterclockwise is positive. But you're totally free to assume the convention you prefer. Do you remember? Then, what do we have? We have HB, but again, HB is a horizontal force whose line of action passes through point A, therefore no contribution. The only thing that is left is BB, whose lever arm is simply L, the length of the beam. Its moment is counterclockwise, and therefore minus VB times L equals 0, which leads to VB equal to PL divided by 2. And contradict me if I'm wrong, but isn't this the result we always get when we study a simply supported beam? It is. Spoiler, it is. Check your notes. It was probably one of the first structures I solved to you to show you what a statically determinate structure is. Simply supported beam is like the statically determinate structure together with a cantilever. These are the most simple systems we can think about when we think about statically determinate systems. And the result is like this. Could it have been said in advance? Clearly, yes, because this structure or this substructure is symmetrical. once again, hinge, geometry symmetric, there are no variations, it's a homogeneous section. The load is symmetrically distributed, so I expect the load to go half on one side and half on the other. Okay?
I have a question.
Go ahead.
Okay, if the beam was just a beam with two hinges and it's not connected to anything, it makes sense to me. But I mean, I agree with the calculations. But if I want to,
Thank God.
I agree with the calculations, but logically, speaking, like I would, if I look at this, okay, not the section, the whole thing, I might ask myself, okay, maybe it's not as okay, directly I see PL, so it's gonna be over 2 because the truss, what if the truss member is like it's attached to the hinge? What if it's contributing to part? What if it's lifting part of PL? So how can I?
But that's the problem. It's not a matter of logic. I mean, your problem is the problem that young Patrick faced. I mean, when I first looked at this structure, so it's a good point. One would look at this and without writing the equations would say, why would it be the same as a simply supported beam, since it doesn't look like a simply supported beam? And that's exactly my point. So my point is to show to you that no matter what happens in the surroundings, when you have hinge and hinge, it doesn't matter what you have outside the hinges. That portion of the beam will always work as a simply supported beam. But I could show you many examples. If you've gone to WeBeep, or if you think about what I've shown to you when we first talked about trusses, I showed you the big bridge in Edinburgh, the fourth bridge. Okay, fourth bridge has a structure which looks like this. I'm sketching it very roughly. So it has big trusses here. So it will be, I don't know, like this. Then there is another one here, okay, another big truss where the supports are. So here are the supports, here is another support, and here there will be trusses like this. I'm sketching it very roughly. I'm just saying it's a truss. And then here in the middle you have a smaller truss which is like this. Now, besides the fact that this is a truss, its global behavior is much like a simply supported beam. It will behave as a simply supported beam. So I will expect that if I represent it as a single member, it will have a bending moment that is like this, a shear force that is like this, okay? And of course, when I then go into the truss, it will behave in a different way because it's not a continuous, a simple member, but it's a truss. But this is a basic concept. Other example, you may be familiar with the bridge that failed in Genova some years ago, okay? The Morandi Bridge. Morandi Bridge was exactly the same. The concept was exactly the same. We had big antennas where the supports were, then there were those ties that kept up the bridge, and in the middle was a smaller portion of concrete which was basically put there and simply supported. And that is why it failed. As a matter of fact, it was conceived in such a way that it was statically determinate, so the failure of one member determined the failure of the whole structure, because that's what statically determinate structure are subjected to. When something fails, everything fails. Okay? So, coming back to your question, your point is totally reasonable. There is, looking at the structure, no reason why that beam AB would be exactly the same as a simply supported beam. To convince you about that, I'm writing equations. That's the most simple way to go, because one would say, like Rima does, why would half of the load go here and half of the load go there? Why? That is why.
What if we remove this side and keep
structure becomes unstable.
Why? No, I thought it didn't contribute to the load of the simply supported beam.
It contributes. Who gives PL divided by 2? Who supports beam AB at B?
The hinge?
The hinge which is connected to
The tie, but it's also connected to C, which is connected to a tie.
Yes. So the tie supports both this and this. A structure which consists, just to give you another indication, a structure consisting, let's suppose we remove the tie. A structure consisting of 1, 2, 3 hinges aligned is not stable. Try it. This is the what? Try it. You have to try and solve it. 3 hinges aligned with any load, whatever, whatsoever, of course, vertical load. Try and solve it. You will not be able to write equilibrium equations. Try it.
Right now? Oh.
If you stick to our usual assumptions, this is the most excellent example of an unstable structure, which is 3 hinges aligned. Generally speaking, a system consisting of 2 beams with 3 hinges is another statically determinate structure. But the most important condition is that the 3 hinges are not aligned. Otherwise, it's not stable. Okay? Now, going on, MA equal to 0 gives me that. I could write 2 different equations to work out VA. I could write MB equal to 0, and I would basically rewrite this equation, only replacing VB with VA. This is a possible choice. Or Ry equal to 0, which gives me what? Well, if the total load applied is PL and half of the load goes there, then half of the load must go here. So the conclusion of both these equations is PL divided by 2. And then, what do I have? Here comes the difference. Here comes the difference. If I have HA here and HB here, and I have only one equation left, which is horizontal equilibrium, the only thing I can say is that HA plus HB is equal to 0. Okay? This is the only thing that makes this beam different from a simply supported beam. There can be an axial force. We will then come back to it and show it 0. But the only difference between any beam that has 2 hinges is the axial force. Okay?
Doesn't this equation tell us that they should be opposite in direction?
Of course. Yes. This is the meaning. So HA equal to minus HB means I have to reverse this one, which is a basic condition. So the two should make themselves equilibrium. Or if you want HB equal to minus HA, so I reverse it and I call it HA. But then that's it. I cannot determine its value. The only thing I know about this axial force is that the two have to be equal in value, opposite in sign, but the value remains unknown. Have to work it out some other way. Now let's go to the second beam, which is BC. And I said differently from what I did in the exam. Let's call the span not only L divided by 2, but let's call it L prime. This is P. This is L prime. Now, I could repeat exactly what I said previously. So we will have HB, okay? I already used HB, okay? So I will not use HB, I will use H prime B. HC, okay? And then V prime B, because I already used the VB, and VC, okay? Now, give me credit on this, but I think you may agree. Apart from the fact that there we have L prime, and here we have L, I could write exactly the same equations I previously wrote. So I'm going directly to the conclusions, which are V prime B will be equal to P L prime divided by 2. Half of the load goes to the left. Now replacing and knowing that L prime is equal to L divided by 2, and to make it comparable to what I obtained before, this becomes PL divided by 4. And so is BC. BC is PL divided by 4. And that's it. And again, looking at the horizontal equilibrium, the only thing I can say is what? That H prime B plus HC has to be equal to 0. Otherwise, this beam will move in the horizontal direction. And that's it. Are the results reasonable? Clearly, yes. Also, this beam is symmetric. The share of load that goes to the two ends is the same. Beam is symmetric, okay? The value of V prime B and VC is exactly half of the previous reaction forces I obtained. Why? Because the span is the half. So this is L divided by 2, this is L. So everything is very reasonable.
Professor?
Tell me.
Would it be, can you say the same thing if this one was connected like this and this one like this? Same thing, like you can say this is simply supported, this is simply supported?
What do you think?
I think yes, because this eventually will have vertical and horizontal components.
Well, my answer is simply, as I previously said, doesn't matter whether this tie is vertical or diagonal. The only thing that matters is that this goes from a hinge to a hinge, and that this goes from a hinge to a hinge.
Okay. I don't know, it's very suspicious.
Yes, but you have to try it out with equations. In any case, no matter what, even if we engineers try hard to make elements straight and vertical, you always want diagonal stuff. You architects. Okay, before I go into the bending moment diagrams of or before I go into the internal forces diagrams, let's have a look at the vertical members, okay? A wise choice when you have these type of structures is always looking at how the members look like. That's what I did with the two horizontal members, looking at them, seeing they were straight and constrained to the rest of the structure by means of hinges. I concluded, as regards the shear force, and then we will see the bending moment, they are very much like simply supported. Let's now look at the two vertical members. Again, we have two members which are hinge-hinge. They are straight. They have no load applied. Basically means they are subjected to axial force only, okay? And this greatly reduces the burden of calculations for you. Because, for example, looking at point E, knowing it's a hinge, I would have to say a priori, I expect to have a PE force and an HE force. Knowing it's a truss member, I can immediately say, okay, HE is equal to 0, only axial forces. If you don't realize this, you can always prove it by means of equations. How? So we have member CE, this is C, this is E. I didn't realize it's a truss member, so I put here HE and VE. Okay? And then here I will have what? a VC and an HC are sticking to that, yes, because of the principle of action and reaction, VC, HC, HE, and V. What is a very convenient equation to write on this member? Again, when you have hinges, use them. Right, rotation, equilibrium. Also on parts of the structure. It's very convenient. It's what I basically did there and what I implicitly did there. And in this case, one very convenient equation is the moment with respect to C equal to 0. No contribution from HC, no contribution from VC, no contribution from VE. The only contribution is HE. So HE times the lever arm is H, capital H, standing for height, equal to what? 0. It's the only force acting. There are no loads in the middle. So HE times capital H equal to 0 immediately tells you HE equal 0. And if HE is equal to 0, what will happen to HC? It has to be equal to 0 as well. How can I get it? Here I wrote a rotation equilibrium. I could write a horizontal equilibrium, and I would get HC equals 0. And now let's go back. HC is the horizontal force at the top of the vertical member to the right. For the principle of action and reaction, it is this force here, okay? They basically exchange forces at that point. If it is 0 on the vertical member, it's 0 also here, okay? And if this equation holds, so the two have to be equal, this is 0 as well, okay? And now let's close the circle. We know we have VC, which is equal to PL divided by 4. For the principle of action and reaction, VC acts here at the top of the column, so I can immediately write that this is equal to PL divided by 4. And what will VE be? VC pulling, pushing downwards, VE pushing upwards. For equilibrium, this is equal to PL divided by 4. Okay?
Sorry, Professor, can I have a question?
Go ahead.
Why H we assume is 0 when we have equilibrium, when we calculate the moment, and so why, and it is HE times H, why we assume H is 0 in here?
No, I didn't assume H is 0. H
Okay.
is exactly because this is a number. In our case, it was given later on. H is equal to didn't write it. Whatever. Okay, H is a number. It's not 0. This is different from 0.
Okay.
And that is why this is equal to 0. Because if you have a product of two numbers where one is not 0, the other has to be 0. In Italian, we call it legge di annullamento. Okay? Which means product of two numbers is 0. Either one is 0 or the other is 0.
Or both.
Hmm?
Or both.
Or both.
Thank you very much.
You're welcome.
Professor, in this case, HB and HA are both 0, right?
H?
HB and HA.
I didn't say anything about HA.
But they should be.
Wait,
shouldn't they?
wait.
Because this tie is the same as that tie.
Wait. No spoiler, please. Now we go to the tie. And look at how I'm drawing it. Let's keep the hinge. Let's keep a small portion of the beam to the left, and the small portion to the beam on the right. What do we have, generally speaking, for this tie? A hinge at the top means I expect to have a VD and an HD. Okay? And then what do I have? From the right, nothing in the horizontal direction, okay? I just proved it. Just VB or V prime B, which is over there, it's PL divided by 4. On the beam, it points upwards. For the principle of action and reaction, here it's downwards. And I'm not writing the symbol anymore. Now we know the value, it's PL divided by 4. So I'm writing right away PL divided by 4. On the left, what do we have coming from beam AB? VB, which points upwards on the beam, its value is positive, PL divided by 2. Therefore, here it acts downwards. PL divided by 2. And then what do we have? HB. On the beam, it goes to the right, which means from the principle of action and reaction, I here have to point it to the left. Yes?
If I forget to reverse the direction of VB, what implications does that have?
You have wrong values. And the wrong behavior, because then it would mean this tie is in compression, which is not reasonable and also not consistent with what I wrote. There is a tie, there should be a tie. Okay? Have you got this? Okay? Now, I could repeat exactly what I said here. So, since this is hinge and hinge, the two horizontal forces acting at the extremity have to be 0. If you're not convinced about it, write equilibrium equation, rotation equilibrium about point D. No force will contribute other than HB, which then has to be equal to 0. Okay? In the text, I didn't give the length of the tie. Why? Because it doesn't play a role. You can call it A, you can call it B, you can call it whatever. It only matters if you have to write this rotation equilibrium. But if you see from the beginning that this is a truss member, you will immediately conclude that this is 0 and this is 0. And then going back, this will be equal to 0. And since this equation holds, HA plus HB equal to 0, if this is 0, this is 0. Okay? Finally, 0, 0. What is VD? VD pulling the tie upwards. PL divided by 2, PL divided by 4, pulling it downwards. Obvious conclusion, this is PL divided by 2 plus PL divided by 4 equal to 3 divided by 4 PL. And that's it. Everything clear? Here, assuming that in class you did in another way, so you started from the reaction forces and then went into the single members, I did the opposite. I only looked at the single members. Remember, the basic assumption we have in equilibrium of structures is if a structure is in equilibrium, every single part of the structure is in equilibrium. Okay? Question, either from you or from the people listening from home. Now let's go to the reaction forces. What are the reaction forces? Here, VA is a reaction force. PL divided by 2. Here, at the bottom, we only have a V, which I just erased. Its value is PL divided by 4. Here, at the summit of the die, we have 3 divided by 4 PL. Is the structure in equilibrium? Of course it is. Try it. Let's try one equation, just one. Let's write the vertical translation. So I'm asking myself, Ry equal to 0. Is it true for the whole structure? What do we have? We have 3 forces going upwards. PL divided by 2, 3/4 PL divided by 4. Okay? So I have PL divided by 2 plus 3/4 PL plus PL divided by 4. All the 3 upwards. Minus, what is the resultant force of this load here? It's PL. What is the resultant force of this load? PL divided by 2. So I subtract PL minus PL divided by 2 equal to what? 3/4 plus 1/4 is 1, plus 1 divided by 2 is 3 divided by 2, minus 1 is PL divided by 2, minus PL divided by 2 equal to 0. Check. Okay?
The PL of the 4 that we wrote at the bottom is the PL of the 4 we calculated by assuming that this is a supported beam. And we translated it down because hinges transfer.
Yes, we did some passages in between. So I didn't directly translate VC to the bottom. I put it at the top of the column, and then looking at the column, I consider that if there is a load downwards on the top, there will be a load upwards at the bottom by axial equilibrium. Okay? Do we need another equation? Well, horizontal equilibrium is obvious. There is nothing in the horizontal direction, and there are no reaction forces in the horizontal direction. Okay? You could write a moment equilibrium. Pick a point. Pick a point. This is A, B, C, D, E. What?
E.
E. So let's check whether equilibrium holds by writing ME equal to 0. I don't know whether it holds, so I'm putting the question mark. So with respect to E, I have what? PL divided by 2 times L divided by 4. This is half of the span. So I have PL divided by 2 times L divided by 4. Note that in this case, putting this contribution positive means I'm implicitly assuming counterclockwise is positive. Because with respect to this point, this is counterclockwise. Okay? Then I have 3/4 PL, whose lever arm is L divided by 2. This is clockwise. So I have minus 3/4 PL times L divided by 2. Then I have this one. What is the lever arm of this one? It's L divided by 2 plus L divided by 2. So it's L. Its contribution is much like this one, so it's counterclockwise. So I will put here plus PL times L. Last but not least, I have this PL divided by 2, whose lever arm is L plus L divided by 2. So minus, because it's clockwise, PL divided by 2 times 3 divided by 2 PL. This is PL squared divided by 8. This is 3/8 PL squared. This is PL squared. And this is 3/4 PL squared. So if you have PL squared divided by 8 minus 3/8 PL squared, it gives you minus PL squared divided by 4. Okay? Plus PL squared gives you 3/4 PL squared. Minus 3/4 PL squared gives you 0. Check. Tell me.
Why you have the extra P at the three? There was a
Mistake. It's non-correct from the dimensional point of view. L can be square, P can never be square. Okay? It was a mistake. Got it? If you're not convinced, once again, try any other point. And I invite you to do it, not only with respect to the points which are inside the structure. Try this point here. L to the left of A, whether rotation equilibrium holds. It will, believe me. So you can either trust me and believe me, or you can try it yourself. But you will see it works.
I have a general question.
Tell me.
So, if you're doing the moment equation, if you're doing the moment equation, you don't take the forces that are on that point.
No.
Why?
Because the lever arm is. The moment is always the problem between the force and the lever arm. But if the force is applied at the point where calculating the reference point for the calculation of the moment, or when the line of action of the force passes through the point which you use to calculate the moment, then its contribution is. Okay?
It's like how if you sit in the middle of a seesaw, right? It will not rotate. If you sit in the middle of the seesaw, right? If you sit in the middle, you're at the.
You don't have a you don't displace vertically, you simply rotate like this.
If
So
you're in the middle, you shouldn't rotate.
no, you rotate. Try it. There is a nice playing ground in.
Okay, then
Yes,
it's
the one.
like if you have a door handle, but you're pressing on the knob instead of the handle.
That's a better example. To open up the door handle, you need a moment. You need to make it rotate. If you pull where the knob handle goes inside the door, you don't make it rotate. Good point. Are we done with this? Can we go into internal forces? Okay. Why did I do this? Because when you have statically determinate structures, checking the equilibrium is a way to know whether you're right or wrong. If you did everything correctly, then everything should coincide, okay? It's not the case with statically indeterminate structures. You could find a solution which is in equilibrium, but which is not the correct one. So now, diagram of the internal force. What will it be? I assume positive tension, so rectangle on the tie, the value is plus 3/4 PL. Negative on the column minus PL divided by 4. The ratio between the two is 3. Now the shear force diagram you have the results in your hand. You know that on B maybe you have a clockwise shear, which is PL divided by 2 to the left, a counterclockwise shear to the right. How will it vary in the middle? Straight line. When you have a distributed load, shear force diagram is a straight line. So from PL divided by 2 positive to minus PL2 to the right, in between it's a straight line. This is a positive portion, this is a negative portion. It cannot be in other ways, okay? And you could have told from the beginning, to have a beam, no matter what forces, shear forces you have at the ends, shear force diagram is straight line, okay? If you have a distributed load and no other loads apply, it's a straight line, continuous straight line.
I have a question.
Tell me?
May I?
Yes.
And other questions we have when we have a point and forces on the left and right, you will have, for example, shear on this side and shear on this side.
Plotted like this is not clear.
Okay, let me elaborate. So you have two, like the shear is the combination of these two internal shears. I don't know how
You're
to call
talking
them.
about reaction force.
Yeah, okay.
Not about shear.
Reaction. This is the reaction force?
Yes.
Okay. It's a combination of, what do we call these?
I don't understand what you mean.
Okay, in this case, for example, you have PL over 2 and PL over 4.
Yes.
That's why the total is 3 over 4 PL, right? What do I call PL over 2, PL over 4?
Shear force.
Okay, so they have a reaction force, which is a combination of these two shear forces.
Yes, but this is not the general way to say it.
Okay.
So I don't like it.
Okay. I will fix that, but let me get to the question.
Yeah.
So usually when we have this in complete structures, we would end up, when we draw the shear, let me draw it off the no, never mind. When we draw the shear, we would go like this, and then it would be something like this, where this would be PL over 2, this would be PL over 4, and this would be P over 4 PL.
Yeah.
You remember the question I'm talking about?
Of course.
So in this case, why is it only 1?
Because I wasn't finished with drawing the diagram.
Oh. Oops.
I'm only halfway on the exercise. What happens on the beam to the right? Guess what? PL divided by 2 here, PL divided by 4 here. It's, again, positive, because if you look at what we did previously, on the left you have a clockwise shear. To the right of the beam BC, you have a counterclockwise shear. So it goes from positive to negative. This is plus, this is minus, this is PL divided by 4, this is minus PL divided by 4. Actually, here I'm being a little bit redundant. So I'm putting the plus here, the minus here, and another minus here. If you put minus here and then you write PL divided by 2, it's okay anyway, okay? Once you have specified that everything here is negative, I can clearly understand. And guess what? Guess what? This value here, the sum of the two is exactly 3 divided by 4 PL. So the force in the tie. The force in the tie, the concentrated force in the tie produces a discontinuity. That is why we have that jump, okay? This is typical, and as your colleague mentioned, you also see it in continuous beams when you have a support. But as a matter of fact, the tie we have here is nothing more than a support for the two beams. It supports, by working in tension, the two beams, prevents them from displacing, takes the forces coming from the two beams. Nothing else. This is 0, this is 0. I forgot to put it here, 0 and 0. Now, to the bending moment.
We don't have to draw a line, right?
What line?
Like a line that resembles the tie for the shear diagram. The vertical line.
There is no shear force in the tie.
Yeah, but like, is it wrong if I don't draw that line where the tie is?
Yes.
It is?
Yes.
Why?
Because I don't like it. When you plot internal forces diagrams, you have all the members, also those which are not subjected to internal forces. And besides, suppose that I did the same you said on that. So I get rid of the horizontal beam. What do I see? I see a straight line, then I see nothing, then I see another straight line. I don't know what I'm looking at.
What line?
I was referring to the vertical line.
Yes, so let me elaborate and correct me if I'm wrong, Rima. She says, if this member has 0 axial force and this member has 0 axial force, do I have to draw them? My answer is yes, because I want to see the whole structure, and exactly by highlighting the fact that there are rectangles here and that there is nothing here, I immediately see what the members which are subjected to axial forces are. The same here. So, answer simple and straight. When you plot internal forces diagrams, draw all the members, even if they are subjected to an internal force which is 0. In which case, that's what we usually plot to say it's 0. 2 things. Tell me.
There are the same directions. So why did one diagram is one line?
The axial force.
Yeah,
One is tension, one is compression. Tie column. Again, my convention, which is highlighted to the top left, is positive is tension. You can also say positive is compression. Important thing is, again, consistency. Okay?
Shouldn't they be the opposites of each other because one is positive and one is negative?
Which one?
The actual forces, they're both in the same direction.
You mean the rectangle, one be to the left, one be to the right of the vertical line?
I don't get your point, sorry.
Like, shouldn't it be the opposite? One is going this way, one is going that way.
Ah, for the side? No, that's not relevant. The side that I use to plot the diagrams is not relevant.
As long as you put the plus and minus.
When I specify the sign, it becomes not relevant. Clearly, in this case, plotting this to the bottom would be a little bit misleading, okay? But again, if you specify it's plus and you are consistent with the convention, it's the sign that matters, okay? Finally, the bending moment. A bending moment, what shape does it have? Before doing calculations,
Two smiley faces.
basically, yes, but from the mathematical point of view, I know that when there is a beam subjected to distributed load, moment should be continuous and parabolic. Moreover, both on this beam and on this beam, I know it's starting from 0 and it's ending at 0, okay?
What do you mean continuous, Professor?
It's a mathematical concept. This shear force plot is not continuous because it has a jump, okay? Continuous plot is a plot where there are no differences at one point between the value to the left and the value to the right. This is a discontinuous plot.
How does the moment diagram, how is the moment diagram continuous?
Well, it can be proven mathematically. It is continuous.
So it's not about the shape of the graph?
Yes, we will see. I mean, you will not see any point where the values are different to the left and to the right. It's continuous, that is continuous. Here, on the contrary, for the shear force, if you are to the left, you have minus PL divided by 2. To the right, you have PL divided by 4. So there is a jump, okay?
Yeah.
In the bending moment diagram, this does not happen. And we can see it from the beginning because we know it's 0 here, it's 0 here, and it's 0 here, and it's 0 everywhere here and here because these are truss members. How will the shape be? Don't let me go through all the calculations, I want to go on, but let me just say, it's a parabola, has to be symmetric because structure is symmetric. So there will be a maximum point where the shear force is 0, which happens at midspan in both beams, okay? So the shape will be like this. 1, and 2. The value which is most relevant is clearly the maximum value. And the maximum value, you can work it out by means of simple calculation. Basically, you have to work out the bending moment and midspan. I'm showing you an example. On AB, I know that to the left we have a PL divided by 2. I take half of the beam, L divided by 2. This is the value of the load, P. And here you have M maximum.
We're assuming that Max is at the middle because it's simply supported beam.
No, because the shear force is 0 there.
No, how do you know that it's 0 in the middle of the beam?
The shear force. First of all, because if it starts from PL divided by 2 and it goes to minus PL divided by 2, it will be there. But by writing equations, you could also end up with the same.
I would rather not.
Okay. Fair enough. M max. What is M max? This is counterclockwise. If I write equilibrium equation, rotation with respect to this point, I have this, which is counterclockwise. This PL divided by 2 is clockwise. So I'm writing directly PL divided by 2 times L divided by 2. And then I have this contribution, which is PL divided by 2, whose lever arm is clearly L divided by 4, minus PL divided by 2 times L divided by 4. This gives you PL squared divided by 8. So this value will be PL squared divided by 8. If you repeat the calculation on the second beam, which is BC, just to make it simpler, stick to what I did before. On BC,
Is that BS squared over 16?
wait. Remember, I said the span the length of the span BC is L divided by 2. But suppose I called it L prime. What would the maximum bending moment be? Similarly to this, it would be PL prime to the power of 2 divided by 8. Then by replacing PL prime is L divided by 2 to the power of 2 divided by 8. Summing up, it gives you PL square. This becomes 4 multiplied by 8. It's 32. So PL square divided by 32. This is the value. Does it make sense? It makes sense because if you see, the maximum bending moment depends on the square of the span. If you have a square span, which is double another square, another span again, the bending moment, the maximum bending moment is 4 times bigger. 8, 32.
When you say square, you mean like area rather than like
No, a square I means these two which happens here.
Why?
PL square.
Why does anything this way? Theoretically.
Why?
I mean, why is moment?
PL square divided by 8.
I mean, what makes moment different so that when we are dealing with shear, we're only like dividing like it's half, but here it's over 4.
Because the bending moment is a force times a lever arm. PL divided by 2 is force.
Because our force is an
This
expression that uses distance.
Yeah, because in this case, both the force and the lever arm, they depend on L. That's what makes the bending moment dependent on L square.
What if our force was given as a number rather than as an expression? Do we still need to divide by 4? Because we wouldn't have L.
No, I'm not. No. Let's not give general rules. This happens because we have distributed loads. Concentrated force, different stuff. Okay?
No.
But you can try. You can look at what happens on a simply supported beam with a concentrated force in the middle. Maximum moment is PL divided by 4. Okay, PL divided by 4. So what happens if I double the span? Will the moment double or increase by 4 times? Yes. So different force, different story. Everything clear about this? Now, let's go back to where we started. Look at these bending moment diagrams, look at these shear force diagrams. Are they any different from shear force bending moment diagram and shear force diagram of a simply supported beam?
No.
No, of course not. Of course not.
Except for the antennas.
Except for the tying column. I don't know if I asked you here to plot the deformed shape. No, because it was trivial. So let's go now into the numbers in the time we have left. So I'm going to get rid of this blackboard first. So here a certain number of data were given. I will just recall them here. L is equal to 5 meters.
Are we designing in this question?
Yes. PSLS, meaning serviceability limit state, is equal to 20 kilonewton over meter. Let's stop here. First question was, design the section of beam AD at SLS, meaning use this load here, assuming an IPE profile, so we use a section which is the standard section IPE, by limiting the maximum displacement at midspan to Vmax L divided by 350. The modulus of elasticity of the steel is ES 200 gigapascals. So another datum which we need is ES 200 gigapascals. And the task is Vmax, meaning displacement, lower equal to L divided by 350. Okay? Meaning, translation of this problem. We know we have two basically simply supported beams. We know they're going to deflect under the applied load. We want to limit the deflection by thereby meaning the displacement, the maximum displacement, which takes place at midspan, to this value here. How much is this value? L is 5, 350. Somebody do the calculation, or I can do the calculation. I have my calculator. $500 divided by 350, 143 centimeters. Okay, just to give you a number. How do I get to this? This is 5 meters, so 500 centimeters dividing by 350 gives you 1.43. Okay? How do I do that? I have design aids. This is what you had during the exam. Coefficient for simply supported beam. I will replot it here. Tells you that a simply supported beam subjected to a distributed load, which is P, when the length is L and the bending stiffness is EJ, has a maximum deflection whose value is 5 divided by 384 times PL to the power of 4 divided by EJ. So, knowing this info, having this data, you have to determine what? The task is design the section. So you have to identify which is the only unknown I have available. Let's look at this expression. These are numbers. P load is given. Span is given. Elasticity modulus is given. What is not given is this one. Second order moment of area. When you pick a section, and you have to choose it, for all the different sections, you always have the info concerning, for example, the second order moment of area. So what will the design task be? Knowing this equation, knowing this limiting condition, I will work out the minimum second order moment of area I need to fulfill the design task. How? If this is the displacement, so if my displacement under the applied load is this, I need to make sure that this number is lower than what? L divided by 350. Agree? How can I do that? Simply by working out the minimum value of J. So have to bring this up here and all this to the left. So this equation translates into J larger than 5384 times P L to the power of 3 divided by E multiplied by 350. Okay? Here you have to replace the numbers by being very careful, okay, with units of measure. So you have to be consistent because here you have different numbers in different units of measure, okay? For example, it's convenient to transform the gigapascals into kilonewton and meters, because I have meters here, kilonewton over meters here. What are 200 gigapascals in kilonewton meters? Well, 200 gigapascals means 200 times 10 to the power of 9 Newton over square meter. Which means 200 times 10 to the power of 6 kilonewtons over square meter. Okay? In this way, this is consistent with this and with this. Everything is in kilonewtons and meters. Let's do the calculation. J should be larger than 5 divided by 384 times 20 times L to the power of 3 is 5 to the power of 3 divided by E 200 10 to the power of 6 multiplied by 350. This is equal to what? Let me do it. 5 divided by 384 times 20 times 5 times 5 times 5 divided by 200 divided by 1,000,000 times 350. So the number I get, careful with the digits, is 0.0005697. What are the units of measure? I'm working out a second order moment of area which has the units of measure which is a length to the power of 4. Since I work with meters, this is m to the power of 4. How do I come up with centimeters? How do I transform it into centimeters? How many centimeters are there?
100 to the power of 4?
Yes, I multiply by 100 to the power of 4. This means by 100 by 100 by 100 by 100.
10 million?
Result is 5697 centimeters to the power of 4. Why did I go into centimeters? Because in the table I have my second order moments of area expressed in centimeters to the power of 4.
Is there a point between the 9 and 7?
What?
It's 5,697.
Yes. I'm not going into more digits because to do a design task. How do you do the design task? Well, since you know this is the minimum second order moment of area, which allows you to fulfill the design requirement, you pick the first profile, which has a second order moment of area, which is larger. So I'm reading you the numbers. For example, if I have an IP 200, J, here it was called JY, is equal to 1943 too low. If I have an IPE 220, this will be, I'm just writing the number, 2772. If I have an IPE 240, 3892. If I have an IPE 270, 5790. That's the one. I don't need to go any larger because this is sufficient. And note that 5790 is larger than and this one with some margin, which is good. I'm not exactly at the limit, I'm a little bit lower. And that's okay. For design purposes, such an approach is okay. Got it? Second task. Tell me.
What changes in a beam, in an I-beam, as its IPE increases? The properties. I don't mean like J, I don't know what, I mean.
Physically, if you say you have an IPE section, IPE 220, this means that you have a beam that looks like this. Whereby this is 220 millimeters.
Oh.
Characteristic of the IPE profiles is the fact that they are I-shaped, but the depth is more or less twice the width. Okay?
Does the thickness of the web or the flange change also with the?
Yeah, everything changes. Everything changes, but everything is standardized. For example, if you have other types of profiles, HE beams, they do not look like this. They look more like this. So the width is comparable to the depth. That is why these type of profiles are used in beams, where there is clearly a plane where the flexure works. For columns, this is more used, okay? Because in columns, generally speaking, you can have flexure in both directions. In any case, you need, for the same dimensions, you need stronger profiles because you have the compression effect and you want to be sure in the case of buckling, okay?
This is about like strong axis, weak axis.
There is always strong axis and weak axis. Simply for the same depth, I make the flange larger because I want it to be a little bit more performing when it's used for columns. But there is no rule about it. When you're the designer, you're king. The only thing you matter about is, or there are two things you matter about. You worry about, sorry. One is first and foremost safety. Second one is
Comfort.
no.
Shape.
It's included in the safety. Safety for SLS means comfort. Such a requirement, for example, the one we just designed is a way of making sure the beam is comfortable. So when you walk on it, it doesn't vibrate too much. Now the other one is very, let me be very, very materialistic or material. It's money. That's why when I pick the profile, I stop as soon as I have the number. I'm not going on to look for larger profiles. Okay? Because a larger profile means higher weight and more money. And let me be clear about this, about it. It's nothing wrong with this, okay? That makes the difference between somebody that can perform structural design and somebody who cannot. Okay? We're not building like they did in the Middle Ages or like they did in Roman times, okay? We're trying to optimize the materials. That's perfectly reasonable, okay? Some would say sustainability. Not convinced that it's a matter of sustainability. I think it's about money, my opinion. But it's perfectly reasonable. I mean,
Why not both? Why not both?
That's your task. I'm old, you're young.
I thought
Your
you were
task
going
too.
to say the second factor is aesthetics.
That's another of your tasks. So you have to build nice, sustainable, and optimized structures.
I thought you would say sustainability and money are the same thing.
In some way, yes. The more material you use, the more you consume, the more resources you need, and it also costs more. Yes, in some way they are related. But clearly, when I'm not, it's simply I want to be honest to you. when I look at the design and when I do the design the way I did here, it's not sustainability that I have in mind, okay? I'm thinking about something else, okay? For example, one could argue, do not teach us about steel, because steel is a very energy, labor intensive product, so you should go into something else, some biomaterials or something like that. Okay, that would be something more focused on sustainability. So I want to be honest with you. It's not. But it's because that's important, because it's not your money, so it's somebody else's money. If you're too costly, you don't get the job. It's simple. Second task. The second task, which was task D, said, check the bending capacity of beam BC, the second one, at the ULS. So it's talking now about ultimate limit states, which means totally different story. Here we design for displacements. As she pointed out, we want our structure to be usable. So when you walk on the beam, doesn't vibrate too much, you don't feel dizzy, you don't feel seasick. You can use it in a comfortable way. When I'm asking about ultimate limit states, I'm simply saying make sure that under the given loads or under the loaded ultimate limit states, the beam does not collapse. Okay? Now, the datum you need here is PULS. Is equal to what? 30 kilonewton meter. Okay? If it says check the bending capacity, I'm suggesting don't look at the shear, just look at the bending moment. Now, we know what the maximum bending moment on the beam is. So for beam BC, we've seen it just previously. It's PL squared divided by 32. Replacing the numbers, we have 30 times 5, which is L divided to the power of 2 divided by 32. Number is 30 times 25 divided by 32. 23.4375. Let's make it 24 kilonewton meter. Okay? Look at the units of measure. Kilonewton meter. Force times lever R. Okay? The load is force over a length. A load which is distributed over a length. A force which is smeared over a length. Okay? When you have a section which is an I profile, because in the sketch it was said that the BC beam was an IB 180. When does it collapse? When does it reach its ultimate limit state in bending? Go back to the notes when we talked about bending capacity. You remember there is this phenomenon called redistribution. So starting from a linear distribution of stresses, we redistribute up to the point where all the fibers are working at their maximum stress, which is the yield strength, with a distribution that has to comply with the fact that we are talking about bending. Summing up, look up the notes. I expect to have a distribution of stresses which is like this. Top is in compression, bottom is in tension. all the fibers have the same value of stress, which is the maximum stress they can sustain. In the design phase, this would be FYD. The moment which corresponds to such a distribution is called mu or M plastic, resistant, like this. Doesn't matter about the symbol. The important thing is to remember what its expression is. Given FYD, yield strength, the value of the maximum bending moment the section can develop is FYD times a certain geometric property, which we call plastic section modulus. This was all explained during class. We can call it WPLY, and Y is there not because of yield, but because of the axis we are considering, bending about strong axis. In this case, it is different from the previous one. We know this was given, we know the section. So what we have to do is simply look up in the table what the plastic section modulus for IP 180 is. Here it says 166.4 centimeters to the power of 3. So for IPE 180, WPL Y is 166.4 cubic centimeters. So let's do the calculation. What is FYD? I didn't give it. I give it now. FYD is equal to 220 . So this number becomes, careful again about the units of measure. 220 megapascals means 220 newtons over square millimeter. Okay? So if I work with this number, 220, I have to transform this into cubic millimeters. By doing what? Multiplying it by 1,000. Okay? So 166,400 cubic millimeters. What's the number? $36,608,000. Okay? Since it's a moment, what will the units of measure be? It will be newtons times millimeters. Okay? But I want it in kilonewton times meters. So I have to do another conversion. So this is 366,080,000 Newton millimeters. To go from this to kilonewton times meters, I have to divide by 1,000 because millimeters have to transform in meters. And by another 1,000 because newtons have to go into kilonewtons. So this basically means getting rid of this and putting a comma here, rounding it up or rounding it down because we are working out the resistance, so it's wise to round it down. Okay, 36 divided 36,6 becomes 36 kilonewton meters. Still much larger than this one, so the check is okay. Got it? Is there something you didn't understand?
Yes.
Tell me.
When we are calculating the deflection displacement, we check the maximum displacement that the beam can withstand. We calculate the displacement that's happening. We see if it's less than the maximum one the beam can withstand. And so we say, okay, this works well. Here, we calculate the maximum moment the beam can withstand. So now shouldn't this value, which is the moment that the beam is under with certain load. Shouldn't this number be less than that, not greater?
No,
But
this
I
is
feel
the
like
mo
we
this
need to-
no, this is the moment which the beam is subjected to. This is the maximum bending moment the beam can withstand. So this number here comes from this reasoning. If I have an IP 180 subjected to flexion, and I exploit each of its fibers to the highest stress, what is the moment that I have? This calculation gives you 36 kilonewton meters. So this is the maximum bending moment an IP 180 can withstand. Question is, if I have a bending moment which is acting on the beam, so this is the acting bending moment, which is lower, or I should say much lower. It's to go from there to there, you need to increase this by 50%. It's a big share. Is it safe or not safe? This is acting. Given the loads, given the design prescription, given the standards or the requirements of the landlord, provided they are higher than the standards, this is the maximum possible load acting on the beam.
How do we know that this is the maximum load that could be acting on the beam?
On the basis of statistics or on the basis of some special considerations. Knowing that we are, for example, in a classroom of a university and assuming you students crowd, we know that there will not be a load higher than 300 kilograms per square meter.
So PULS means the maximum possible
Yes,
load that could
determined by the standards. If you stick to the standard, you don't have to worry about it. Okay? If you're under the umbrella of the standards, it means you're sticking to requirements that were worked out for structures to be safe. Okay?
Do these include safety factors or no?
When I give it to you during the written
I mean,
exam,
not in real life, regardless of the exam.
no, in real life, you have to work out from the basic loads the ultimate limit state load. Just to give you an idea, previously we had 20 kilonewton meters. Okay, it's a serviceability load. If you go into ultimate limit state load, it means it's a load which is much higher, 50% higher. Okay, so which means under service conditions, ordinary service conditions, your structure works. For example, this classroom, 300 kilograms per square meter. I'm inventing, okay? 3 kilonewtons per square meter, okay? Which means students which crowd the room, okay? When I do the ultimate limit states calculation, so I'm looking at the structure to be safe for not failing. I'm not calculating it under 300. I'm calculating it under 450, 500. Much higher load. Because it's an event I want to be very far away from. I don't want to even get close to the possibility of failure. Third task is design the section of tie BD at the ULS. Again, we are designing a tie at ultimate limit states, assuming a circular section with an even diameter. So the section is circular and the diameter should be even. Why do we have only even diameters when we design circular sections?
We have an even load.
No. Come on.
What's the question? Why do we have a circular section?
Now, why do we have a circular section with only even diameters? So we have 12, 14, 16, 18. We don't have 12, 13.
Because the increase, like the property of the tie will not increase much between one digit and another. So because maybe industrially it's easier to produce.
So that when you talk about the radius, you never have to use it.
Other ideas?
I mean, is there really going to be such a difference between 12 and 13? Might as well jump to 14.
That's the point. There is not much difference. So if I tell you, hand me 12 millimeter bars, will you distinguish it from a 13 millimeter bar? It's specifically meant for the working place.
Wow.
Hey, hand me the 12 millimeter bar. If I also have the There were 11 millimeter bars.
But then
That's-
you can also think about it like, what if we run out of 12? Is it better to use 13 than 14 or 10?
No, you use a larger diameter. You use what you have. Okay? Section 1-1 is circle. And the diameter phi is even. We know it's subjected, we've seen it before, it's subjected to a load which is 3/4 PL. What will this load be? 3/4 PL, which is NULS, is equal to 3 divided by 4 times, what is the load at ULS? We have it over there, 30 times 5. How much is that? It's 150 divided by 4. I'm getting bored, not doing the calculation like this. 3/4 times 3/4 times 30 times 5.
Professor, and
Tell me.
in this type of question, you wouldn't ask us to calculate, like, to design the one under compression, would you?
Depends. Can happen.
Would not.
Hope is the last goddess, as we say.
Is the last
Spes ultima dea.
Is the last one?
Goddess. No, God, male. The goddess is female. Hope is the last goddess. 111.75 kilonewtons. How does a tie resist tension? Again, when you have a member which is subjected to pure tension, you pull it, you have a load distribution, stress distribution, where every fiber is exploited to its very maximum, again the yield strength, but differently from what we have above, where the action is bending, when there is pure tension force, all the fibers are the same value of stress, also in terms of sign. So you have a uniform stress distribution, whereby all the fibers work at FYD. This gives you the resistant action force, whose value is simply FYD times A, whereby A is the area of the section. Now, if I have to design, how can I do that? I have to make sure that this NRD, resistant actual force, is larger than this acting actual force, NSD. What is my unknown in this case? It was clearly mentioned. Design the section of the tie BD, so I have to design the area, assuming a circular section with an even diameter. So in the end, my unknown is the diameter. Okay? How do I do the calculation? Again, have to make sure, careful, that this is larger, equal than this. So what will the minimum area be? The minimum area is NSD divided by FYD. Let's do the calculation. This is 111.75 kilonewtons. Knowing that FYD is in newtons over square millimeters, I'm transforming this into newtons. So it's 111.750 divided by 220. What's the number? 111.750 divided by 220. 507.95. Let's round it up to 508 square millimeters. Is this area enough? No. You cannot say to your people working on the structure, okay, put there a tie whose area is 508 square millimeters. Are they supposed to know how to calculate an area? No. I mean, they could, but they are not supposed to do. They are, on the contrary, they know a diameter which is 12, 14, 16, just because if they don't know, it's usually marked. When you have a tie or a circular section member, it's probably written somewhere how much the diameter is. Much like the, how do you call them? The range has a number on top, 12, 13, 14. So what would the diameter be? The minimum? I have to know what the area is. If you have the diameter, the area is P. Diameter to the power of 4, which means my minimum phi is equal to what? Square root of 4a minimum, which is this one, divided by P. Let's do the calculation. So it's 4 times 508 divided by P. 4 times 508 divided by P. 646 is the number under the square root, so I will now make the square root. Final result is 25.432, rounded up 26. It's an even diameter. So instead, since I'm rounding, I'm putting here 26 millimeters. Is it acceptable? How much are 26 millimeters?
How much in what?
How much?
Like size?
Yeah, not bad. Imagine a structural member which is like this. Barely visible. Nice. Got it? Let me check the time. 8 minutes to go. We have to design the column.
You do?
We have, no, not design, checking. So it's easy. Final task is
Professor, just quick check. So NSD is the axial force that's actually happening inside, and NRD.
maximum possible.
Yeah, and NRD is what we are, is the axial force we are designing the tie to withstand. Which, I guess?
Given a member subjected to pure tension with a yield strength which is equal to FOED and an area which is A, NRD is the maximum axial force the member can be subjected to. Okay? Given its properties of material, FOED, and of geometry, A. Knowing this from structural mechanics concepts, I designed the area and therefore the diameter in order to make this number larger than this one, in order to guarantee the safety.
But like in reality, we should never be able to reach this one, right?
Yes. And we will not. There are safety margins. So my material, I design it with a yield strength of 220. The yield strength will not be 220, it will be higher. The load is 30. The service load will never be 30. It will be much lower. That's the same. The likelihood of a structural failure given the usual design procedures in Europe is 10 to the power of -5, which means you risk more when you go hiking in the mountains. So it's more likely that you die, of course it's an example, going in the mountains than by structural failure, okay? Clearly, if the structure is properly designed. If the designer has this number wrong, instead of 3 divided by 4, it's 3 divided by 8 because he got the wrong numbers doing the structural analysis, there's no way. I mean, there is no safety margin against human error, but this is general. It's not only of structural design. We know it. It's the story of humanity. Chernobyl was much like that.
In an office, does anyone check after the engineer?
There is, in Italy, there is a person who is responsible, which means if something goes wrong, serviceability limit states has to pay. If something goes wrong, ultimate limit states he can go to jail because he's responsible for the design. So he takes the full responsibility by signing and stamping. If you go into a job, you are never usually the senior designer, so you're not taking this responsibility. There's a person who is in charge of your work, who's probably experienced, who knows whether there are mistakes simply looking at the structure. More like if I tell you, oh, I designed a concrete beam which is 5 times 5 centimeters. What would you tell me? Come on, it's not a beam.
Yeah, but like an engineer would make not this type of mistake, the type of mistake that would be hard to find if there wasn't.
Yeah, sometimes and sometimes not. I've seen structures fail because there were trivial mistakes. Calculation errors.
Did the engineer go to jail?
I mean, it depends on what happens, on the consequences. If somebody dies, then you can go to jail, of course. Also because there is no way of overcoming. I mean, if something goes wrong as regards serviceability limit states, you pay, maybe you pay a lot, but by paying, you're not convicted. Usually the punishment is money because nobody gets hurt. Okay, it's simply somebody ordered you a product, a structure. The structure is not the way the one who ordered it wanted it. You have to pay him. But much like if you order, I don't know, a coffee machine, the coffee machine comes and it's broken. Okay, you sue the person who sold you the coffee machine. When human life is involved, it's another story. I mean, also the consequences are more severe. Okay. Besides, it's a broad topic. As a university professor, I'm not entitled to do design, and that's it. I mean, I'm not allowed by law to take responsibility.
But you have a PhD.
I have more titles than just a PhD.
And you can't design?
Because of law, because they tell you in Italy, if you are full-time a university professor, do the professor, do not do design.
Why? Because you would be too tired to design properly after, like.
No, because you have to spend time in the university. You have to work with the students. You don't have to waste, between brackets, your time doing design. That makes sense. If you think about it, it makes sense. Doesn't mean we are not involved into design of big structures. You can do it, but making the university aware and always not as the principal person in charge of the design. You can for example, you can be a consultant. So you can tell other people how to design, can give your opinion, and then it's their responsibility to follow your opinion or to do what they want. Okay, that's how it goes. Design the column. Okay, column DE. No, not design again. It's not design. Check. Check because we know the column was to the far right. It is subjected to a load which was PL divided by 4. Coming like this. Okay, this was the load. Okay. Okay, this is the column. The section is, it was specified HE 800. Okay. You don't see the height of the column. Do you have it?
I don't even have a question.
Do you have it? The height of the column?
No. I remember the last time we did it with
Okay, let's say This is h equal to 5 meters, okay? Again, what is the load? The acting load. So this would be called NSD, acting load. It's ultimate limit states 30 times 5 divided by 4. So it will be 150 divided by 4, which is 25. 57, 32.5, I think. So it seems a little bit too low. Let me check. 37.5. Yeah. This is the acting load. If this is the acting load, we need to compare it with the resisting load. Now, the resisting load is NRD FYD times A multiplied by T, a coefficient which takes into account buckling. It is a function of the slenderness, whereby the slenderness we know is buckling length L0 divided by radius of gyration. Okay? Before we put the numbers, let me just tell you that for the HEA profile, we had 3 quantities. The area, 21.24 square centimeters. Second order moment of area about the strong axis, 349.2 centimeters to the power of 4. The other second order moment of area, 133.8 centimeters to the power of 4. I calculate the radius of gyration by this formula, which is J divided by A. Which J do I take? There are 2 choices. What? Since a lower I gives a higher slenderness and therefore an increased risk of buckling, I take for J, Jx, the lower one.
Don't we need less slenderness?
No, less slenderness means lower risk of buckling.
Yeah. Isn't that what we want?
We are not designing, we are checking.
Oh.
To put it in other words.
We're taking the worst case scenario. So
Yes, to put it in other words. If I have such second order moment of area, will this govern buckling or will this govern buckling? Clearly, the weaker link will govern buckling. So it's 133.8 divided by 21.24, 6 to 9, but I have to make the square root, 251. Slenderness becomes L0 if the column is hinge and hinge, is basically H. Tell me. Lambda is L0, so 500 centimeters divided by 251. What happens? This becomes, I doubt it was 500, but okay. It's very high. 200 of slenderness, which table at hand that gives you the omega coefficients is 503. So your key coefficient will be 1 divided 5.03. Basically meaning 1 divided by 5. 0.19. This is the coefficient you need to work out this one. So what would the result be? It will be FOID 220 times 21.24 transformed into millimeters. So in the end, this result will be 220 times 2124 millimeters times 0.2. Result is 20 times 2124 times 2124 times 0.2 divided by 1,000, 93.45 kilonewtons. Larger or lower than this one? Much larger section is okay.